Morning, everyone. My name is Mudasir. Today, I will be presenting my project analysis of global climate indicators through an automated big data pre-processing framework. This project is a part of the data-intensive scalable system module under the guidance of Professor Mohit. This project focuses on designing and implementing a scalable big data pipeline to analyze global climate indicators efficiently. Climate change research produces extremely large and complex data set which are increasingly difficult to process using traditional tools. Manual data processing approaches are not only slow but also error prone and lack scalability, especially when data set grow over time. To address to address this problem, the project proposes an automated end-to-end big data pipeline capable of handling large climate data set efficiently. The main objective of this project were to automate data ingestion, processing, analysis, and storage, perform three analytical studies on global climate data, and use scalable technologies such as Apache Spark, AWS S3, and Postgres SQL. This slide illustrates the overall system architecture and technology stack used in the project. The data flow begins with local CSV file which are uploaded to AWS S3 for scalable cloud storage. Apache Spark is then used for distributed data processing and analysis. The process result are stored in Postgres SQL and final output are exported in CSV and Parquet format. The key technology include Amazon S3 for storage, Spark version 3.5.7 for processing, PostgreSQL 16 for structured persistence, and Python for automation and orchestration. One of the automated pipeline in action. One of the key strength of this project is full automation. We started by ingesting raw global warming data from AWS S3 in Stockholm region, ensuring scalable cloud storage. If S3 is disabled, the pipeline seamlessly switches to local file ingestion. Next, we initiate and optimize Spark session with memory tuning and parallel execution enabled. The required AWS and Postgres SQL connectors are configured for distributed processing. The raw CSV dataset is loaded into a distributed Spark data frame from S3. Spark automatically partitions the 26-column dataset for efficient parallel computation. Data cleaning and pre-processing. We clean the data by handling missing values, standardizing data types, and removing outliers. The processed data is cached and saved in Parquet format for reuse and performance optimization. Climate trend analysis. This stage analyzes long-term climate trend using yearly aggregation and rolling averages. It highlights warming patterns, threshold exceedance, and climate acceleration over time. Analysis economic correlation. Here we examine how economic growth relates to emission and pollution level. Feature scaling and correlation analysis reveal key economic drivers for environmental impact. Uh, Analysis risk classification. We compute composite environmental risk scores using multiple weighted indicators. A random forest model classifies countries into low, medium, or high environmental risk. All clean data and analytical results are stored in the Postgres SQL database. This enables structured querying, reporting, and integration with Power BI tool. Now, the data, finally, the results are exported in CSV, JSON, and Parquet format. These output support visualization, web application, and further big data workflow. The first analysis focused on identifying long-term climate trends. Using Spark, Windows function, and rolling averages, the result clearly shows an accelerating upward trend in global temperature anomalies, supporting existing climate research. The second analysis examined the correlation between economic indicators and emission. Interestingly, the result showed a very weak linear correlation at a global scale, suggesting that the climate impact are influenced by complex, non-linear, and policy-driven factors rather than simple economic growth alone. The third analysis involved machine learning based environmental risk classification. A random forest classifier was trained to predict environmental risk level based on multiple climate indicators. The model achieved a high accuracy of 96.99% and an F1 score of 96.89%, indicating strong predictive performance. The most important predictor identified by the model were extreme weather events and fossil fuels usage, highlighting their significant role in environmental risk assessment. In conclusion, this project successfully delivered a fully automated and scalable climate and data processing pipeline. All academic and technical objectives were met, including automation, scalability, and comprehensive analysis. Key achievement includes single command execution and robust S3, Spark, PostgreSQL architecture, three comprehensive analytical studies, and implementation of the full data lifecycle from ingestion to storage and export. Future work, finally, there are several opportunities for future work. The pipeline could be deployed on Amazon EMR to benchmark performance at a much larger scale. Real-time data ingestion could be added using Apache Kafka, and more advanced machine learning models such as LSTM network could be used for climate forecasting. These enhancements would further strengthen the system applicability to real-world climate analytics. That's all for my project. Thank you.